Okay, so now let's compare why the temperature, the vapor pressure of water versus ethanol is different, more like almost more than twice of each other. Remember there when we talked about water having what? A hydrogen bond between two molecules. Let me actually make this a little bigger. Okay. Okay. So between water molecules, we are seeing this hydrogen bond between oxygen and water, right? And of course, all the other molecules are not drawn here, but there are a bunch of hydrogen bonds going everywhere, right? As long as there's water around it. So it's a whole network of this matrix of water being all check each other with a hydrogen bond. Compared to ethanol, there is a hydrogen bond because this ethanol is C, C, and OH, and the hydrogen being there. Okay, these black ones are the carbons, the white ones are hydrogens, and then O is the one that's representing red, and then oxygen is the white one again. And then because the neighboring of this oxygen is hydrogen and neighboring of that is also oxygen, this actually meets the requirement of hydrogen bond. Okay, so we both have a hydrogen bond between ethanol and water. Why is this? If you look at here, vapor pressure meaning what? How much a liquid is willing to be vaporized. Higher number means you are more willing to be vaporized than the other one is. And it's a lower number. So you can see more than double amount as an ethanol is willing to be vaporized than the water is at a given same temperature. So that means there has to be something that makes a difference between two. Which you are trying to hear is what? Let's differentiate first, okay? Both has hydrogen bond, but what it makes a huge difference is, number one is the number of hydrogen bond that can be associated with from each molecules. I mean, simply drawn here, if what you're seeing here is, okay, there are, but this water molecule has a 4 around it. This oxygen molecule has a 3 around it. Simply of that, but that's actually not only the case. What we have to think about is, this is only drawn in 2-dimensional spaces. You have to think about 3-dimensional. So there could be more than 4 around here. And of course, it could be more than 3 around here too. But what you also think about is the structure that is next to it, which is here. So in terms of water, the whole compound itself is available to form a hydrogen bond with all the waters around it. But here, when you look at here, this is carbon structure where there are not much of polarity exists in this area compared to only this part is where the polarity existed. Okay, so this is a polar region. This is non-polar region. So that creates hindrance of another ethanol. This is an abbreviation of ethanol, ETOH, coming in and try to make bond with these. So this is not a good indication compared to intermolecular force-wise, because this is allows all 4 sides, doesn't matter, 360 degrees, they're all welcome to have a hydrogen bond, where this is a hindering of the hydrogen bond approaching from another molecules. And they are like everywhere in each molecule, except only exposed part of available hydrogen bond is only this part is polar. So it limits the amount of hydrogen bond that can form around it, even though it is available to make hydrogen bond. That creates higher volatility, means what? The attraction force between one molecule to the other molecule is lesser amount than the water is. Therefore, it's easier to break apart from another one. Therefore, your vapor pressure of ethanol is greater than the water because of intermolecular force differences. Okay? Kind of think about it this way, you have a friend who's trying to run away from you, and you have only one of you holding that friend, like an ethanol is, and you have a whole bunch of other friends holding the same person's arm. He's not going anywhere, right? kind of think of a similar way, right? The same strength, but there are more of it makes it stronger altogether compared to there are less. Okay? So that's how we can understand our combining intermolecular forces into how things are more volatile or not. So it's not just a volatility, but it comes with everything that has with something that touches with this molecule too, and that refers to viscosity. Okay. So compare with that also. I mean, here we're talking about honey and water. Let's just kind of go back to ethanol and water also again, right? You have the ETOH, ethanol here, and water. You already know there are more available intermolecular forces as a hydrogen bond with this compared to ethanol is, right? Therefore, you already know which is more easier to flow, because viscosity is what makes it easier to flow. It's this molecule easier to flow, so it's like a so viscosity can be explained as where they are each molecule rubbing against each other or rubbing against another molecule. It could be a straw, it could be a hose, whatever it is, right, when it comes to liquid-wise. So when there's a less amount of intermolecular forces, but here, remember, we had a less amount of intermolecular forces. Okay, I'm just like write as interforce. Compared to this one has a higher intermolecular forces. So you can actually see, even though they are very fluidy liquid, we can already tell this is going to be easier to flow because what? The forces between these molecules among themselves is a lesser strength than water itself, right? So that's how you can tell. So compared to honey and water, that's very obvious. And if you look at, this is a chemical structure of honey. Look at in one molecule, how many OHs are there? And every single OH is where you can have what? Hydrogen bond with another honey molecules. And where water is only this, compared to a whole bunch of them. So look at it, how many hydrogen bonds can actually occur around here compared to this one. That makes why honey is much more thicker, because the intermolecular forces are so many of them in one molecule compared to water. So you can already tell viscosity is going to be as a honey because it's much more thicker compared to water would be. Okay, so this is how you can relate. You're again. Muted. Oh, no, once again muted again. Thank you. Okay, now I can relate how this compared to that in terms of intermolecular forces. Okay, that's why I emphasize intermolecular forces so much, because it relates to almost every subject out there. Okay, all right. So I hope you guys are okay with that topic. And another part that I want to actually discuss about in terms of viscosity is also intermolecular forces related to is two different molecules here. So remember we talked about when we talked about intermolecular forces. We talked about, first of all, the hydrogen bond. Number two was what? Dipole, right? Or dipole moments, dipole forces, doesn't matter. And then we talk about LDF, London dispersion force. Remember how, and this was very unstable, right? When molecules has a spinning of electrons, and these are non-polar molecules, meaning what? The polarity does not really exist until what? Temperatures goes down and becomes a liquid. Means what? Remember, like liquid nitrogens, we talked about that too, right? And here, nitrogens. And usually there are gas states like how oxygen is in room temperature, but when temperature comes down to negative 190 degrees or so, then this becomes liquid. That means what? There is a connection between these two. When electron is spinning in that direction, lower temperature what? Slower movement, right? Therefore, electron will actually spin slower too. So when electrons are on that side, this side is partially negative, causing that side to be partially positive. That attracts that electron toward this way, causing partially negative here, partially positive. At that instant moment, there is a bond between two, which is LDF. This is not stable, so what happens? This electron that was here will flip right back, makes this side partially negative, partially positive, repels that electron that was here also, and electron goes that direction, causing what? Partially positive here, partially negative here, and keeps that bond between two. So it keeps on going back and forth. That's what the LDF is. And they are not really stable until temperatures so low. Now, let's kind of think about it as room temperature. So these two molecules are at room temperature. Okay, so you can see pentane is C5H12 with this long structure, and your dodecane is C12, much longer. And compare that viscosity. Okay, and you see here, first thing you have to notice is what? Everything is carbon and hydrogen. There's not much of polarity exists in here, right? So only four, so if you were to have another pentane next to it, okay, so we have two pentanes next to each other, there is no other real forces between two except what? The weakest, LDF, basically. So that means what? Here, same thing too. Dodecane here, we have a little longer one, and you have another dodecane next to it. Only force if there's anything that's holding to each other is going to be on, once again, LDF. Now, why does this make higher viscosity than this is when the only LDF is there? Let's think about it. How many LDF can be existed in one molecule to the other? You can see there are a whole lot more LDF can be formed as since the surface area is much greater than this one is. So even though LDF itself is a very weak force, because there are multiple of them are piled up on each other, and because the length of the molecules are greater, that makes LDF altogether kind of strong as a lump sum of altogether. So compared to the shorter one, compared to the longer one, this makes better bonding to one molecule to the other compared to that one is. So remember, once again, viscosity is what? A friction between two. Higher force between two will have a higher friction compared to other ones are lower because shorter. Okay. So when you actually see like a gas that you put on a stove, that's like this is. So it's like already in a gas state, so there isn't barely any attraction force between two. It's really hard to put them together unless you go over temperature. But at room temperature it's really hard. But all this organic compound also can be synthetically made or comes organically. But one of the part that we actually consider is coming out from crude oil that we pump it out from the ground way down in the oil rig. So when we actually pull out all that gunk, black gunk out of the ocean, or more like the bottom of the ocean, where below the crust, it's actually a combination of whole different carbon structures. So remember the asphalt that we put on the street, right? On the freeways and whatnot, there are actually all organic structure of a bunch of carbons. So I believe asphalt is like C24 or so, and you can already tell all the asphalts are not. They're not liquid. They're solid, hard like a rock. So if you see like longer chain of carbons, even though they only have LDF as a holding force each other, but if they're long enough, that adds up to become what? Solid state. Okay, so that's another thing you can actually think about. Remember how geckos and all those, microphone was out once again. So all those geckos and all the reptiles can actually stick to the side of walls and ceilings and whatnot is because on their paws and on their body when they're touching on the surface, they have a bunch of fibers that can create the LDF with another surface. So added all that together, if they're strong enough, the attraction force is strong enough for them to stick to the walls. Okay, so LDF is actually quite strong when it comes together as a group of forces altogether. Okay, so that's how you can make actually only LDF make a difference too, not just number of hydrogen bonds, or even different number of dipole forces. Okay, so altogether LDF actually can be much greater. Like, just think about an asphalt, right? Asphalt is actually, in room temperature is a solid, when water, which is hydrogen bond, supposedly stronger as individualized, but water is a liquid state compared to when asphalt is a solid state. Which, I mean, I bet there are more than just a LDF there because with the other substance they put it in, but as a pure carbon chain-wise with the hydrogen bond to it, really greater altogether force of LDF compared to just a water stuff. Okay, so you can see the difference of that when things are added up together. Alrighty, so that's that part.